Okay, class 12. This is one short video that I want to make. Okay, because I felt this was important. Okay, that is to show you the different relations for relative permittivity epsilon r, which is also called dielectric constant. Don't forget. Okay, epsilon r is also called dielectric constant. In some books, of course, dielectric constant is represented by a capital key. All right. Okay, now from definition of dielectric constant, from the very first classes itself, we've learned dielectric constant is epsilon by epsilon naught, where epsilon is the permittivity of a certain medium, okay, and epsilon naught is the permittivity of free space, of course. All right. Okay, now let us consider a capacitor, that is an air capacitor. Okay, we've derived this expression. Okay, we've seen that for an air capacitor, the capacitance is given by epsilon naught A by D. Okay, where the things have the usual meaning, the terms have their usual meaning. Okay, A, of course, is the area of the plates. I didn't want to say, but still, I'm D is the distance between the two plates. Okay, so this is the capacitor. So A is the area of the plates, and D is the separation between the two plates. All right. So this is the equation number 1. All right. Okay, now if the space between the two plates of the capacitor is completely filled with a dielectric material, this space is completely filled up by a dielectric material, then we've seen, okay, dielectric material whose permittivity is epsilon, okay, and its dielectric constant is epsilon r, of course. All right, say for example that dielectric material has permittivity epsilon and its dielectric constant is epsilon r, then the capacitance is given by C dash, which is equal to epsilon r epsilon naught A by D. Okay, in the video that I had made, where this video regarding this thing, capacitance of a capacitor with dielectric slab of thickness T lesser than D, you have to go and check this video first. All right. Okay, so in this video, in this lesson, we've seen that the capacitance of the capacitor, okay, of this capacitor, the capacitance of the capacitor with a dielectric slab in between the two plates, okay, the space not completely filled, was given by this. Go and check this video. It was given by this. All right, now we did two cases when T is equal to D, that is the thickness of the dielectric slab is equal to the separation between the two plates itself. Okay, this is a very, very untidy video. I hope you've understood this derivation. Okay, so in this case, we've seen when T is equal to D, so from this formula, D minus D plus D by epsilon r, this becomes, okay, that is what I've shown over here. D minus D is equal to D by epsilon r. Okay, so we see that the capacitance, when this is the case that we call C dash over here, all right, because this is the expression, this is the notation that I'm using right now. So C dash is the capacitance of the capacitor when the space between the two places is completely filled by the dielectric. So we get epsilon naught epsilon r A by D. Okay, all right, don't get confused with the notations. All right, C dash is for the case when the space between the two places is completely filled up by a dielectric. So we see this, we've derived this. Okay, go and check this video. All right, so so we see when the space between the two places is completely filled by the dielectric, its capacitance is given by epsilon naught epsilon r epsilon naught A by D. All right, so from equations 1 and 2, okay, in fact, dividing equation 2 by equation 1, we see C dash by C is this. All right, from here, okay, epsilon r becomes C dash by C. So epsilon r, the relative permittivity or the permittivity of the medium, okay, dielectric medium, is given by C dash, that is the capacitance of the capacitor. The capacitance of the capacitor when the space between the two plates is completely filled up by a dielectric, divided by the capacitance of the air capacitor. Remember that very capacitor when the space between the two plates is filled by nothing else but air. Okay, all right, so remember this, epsilon r is C dash by C. So this is another relation that we are getting for your relative permittivity. Then for the same capacitor, also for an air capacitor, okay, again air capacitor, the electric field intensity in between the two places given by E is sigma by epsilon naught. So we have this air capacitor. At any point in between the two plates, the electric field between the two places is given by sigma by epsilon naught. That is what we are seeing. All right. Now, if the space between the two, this is my equation 3, by the way. Now, if the space between the two places is filled up by a dielectric material, the same case I'm talking about, the space between the two places is filled up by a dielectric material, then the electric field between the two plates is given by E dash, which is equal to sigma by epsilon. Okay, this epsilon can also be written as sigma by epsilon r into epsilon naught, since from this relation itself. From here, we get epsilon is epsilon r into epsilon naught. So I'm substituting. Okay, so this is my equation number 4. So from equations 3 and 4, we get E by E dash is equal to sigma this. Okay, check the mathematics itself. From where we get epsilon r is E by E dash. Okay. All right, so I'm naming this my equation A, the first equation for relative permittivity. This is my equation A, this is my equation B, all right, and this is my equation C. So from A, B, and C, we get epsilon r is epsilon by epsilon naught, which is equal to C dash by C, which is equal to E by E dash. Okay, all right, remember this relation. You don't need the derivation. Okay, you don't need the derivation. All these things, this is not a derivation also actually. Okay, all these things I have done just to make you understand. All right, just to make you understand how we land up at the different relations for epsilon r. You don't need this derivation. Okay, what you need is, you need to remember this. Okay, because sometimes you might need this in numericals. Okay, all right, that's it. Now, one thing I haven't told you, that is energy stored in a capacitor. Before the lockdown started, okay, when we were having our usual classes, okay, the last topic, if I'm not mistaken, the last topic that I did with you all in the classroom itself is energy stored in a conductor, not a capacitor, energy stored in a conductor. And we had got the expression like, you can go and check the derivation. The potential energy stored in the conductor was half CV squared, which is equal to half QB, okay, not QB, it's half QV, which is half Q squared by C. Okay, I hope I have written the notations, the expressions correctly. Okay, now you sometimes get to derive the energy stored in a capacitor. Okay, you sometimes get to do this derivation in the exam. All right, now the derivation I'm not doing, because the derivation will be exactly the same that we've done for energy stored in a conductor. Exactly the same, everything the same. Only thing is, instead of a conductor, you need to write a capacitor. Instead of a conductor, you will write a capacitor. Every other thing is the same. The integrations that we do, every other thing, how we land up at the integrations, every other thing is the same. Okay, everything. Only thing is, instead of the conductor, you need to write a capacitor. Okay, and you land up at these expressions where C will be the capacitance of the conductor. C in that derivation is the capacitance of the conductor. All right, but here C will be the capacitance of the capacitor. Remember that. Okay, I don't know whether you all are understanding my videos or not. Okay, if you don't understand, of course you can let me know, in that WhatsApp group itself. Okay, any confusion you have, any doubt you have, you can write there in the WhatsApp group itself. Okay, but do let me know if you have some problems. Okay, all right, so this is what I wanted to say about the last thing I wanted to say. Remember this expression. Okay, from next video onwards we'll start electric current. All right, so stay safe. Thank you.